All right, so like I said, we are going to cover 7.5, 7.6, and 7.7, but not in that order. I'm actually going to start with 7.7. It's going to play nicer if we do that. So 7.7 deals with imaginary, or what we call complex numbers. So real quick, I'm going to revisit how to simplify radicals. So again, this is what we did last time. So if I gave you something like the square root of 12 and told you to simplify this, okay, we broke it into its prime factors. 12 is 2 times 6. 6 is 2 times 3. We got a pair of 2's for a square root. That's what comes outside. Any little leftover thing stays inside. So the square root of 12 reduces to 2 square roots of 3. Okay, there's basically another way to do this kind of same thing. If you understand how perfect squares work, we can rewrite the square root of 12 as the square root of 4 times the square root of 3. And the square root of 4 is 2, because 2 times 2 is 4. So then that's another way we can get those 2 square roots of 3. Now, again, where 7.7 comes into play is dealing with imaginary, or what we call complex numbers. As long as you have the square root of a positive, you can end up getting some sort of nice, pretty neat answer. For example, I'll just go back and revisit, like, say, the square root of 4. 4 is 2 times 2, so the square root of 4 is 2. However, at some point in time, they realized that even though the square root of -4 is not real, they needed it to equal something so that they could go back and solve. There are certain things where you actually need complex numbers to solve for some stuff. So they needed something for this. So what they did is they created a number. They call the square root of -1 the letter I. Okay, and what that stands for, again, is the imaginary number. All right, a couple people come in, so I'm going to put them down in here as present, and then we'll keep going. So again, due to the need, they created this number. It's an imaginary number, but they're calling the square root of -1 just an I. It stands for the imaginary number. So now if I was told to simplify the square root of -4, we could rewrite this as the square root of 4 times the square root of -1. Square root of 4 is still 2, and that square root of -1 is I. So now we can simplify the square root of negative numbers, and we can get these imaginary numbers. So that's some of the first things they're going to expect you to be able to do to simplify. So they're going to give you some numbers like the square root of -12. The only thing that changes from what we did before is, okay, if we were going to break down the square root of 12, I still want to break it into its prime factors. 12 is 2 times 6. 6 is 2 times 3. With a square root, I'm still looking for pairs. If I have a pair of 2's, that comes outside. And again, that little leftover 3 stays inside. The only difference is, again, this negative inside of your radical makes your number complex. So now we would have 2i square roots of 3. Now, typically it is considered mathematically correct to put the I here. We kind of treat it like a variable. So we'll put a whole number first and then the I. And then if there's a radical, we put it here. Okay, because the I is outside of the radical. Now, I have a calculator that will simplify imaginary numbers. And when it writes it, it says 2 square roots of 3i, like so. But you've got to be really careful about that because it's got to be outside of the radical. If you get lazy with writing stuff and you write it like that, where it looks like that I is still underneath that radical, the square root of I and an outside I are two different things. So I tend to bring that I out in front so it lacks any confusion. So either of these would be considered right, correct, and we'll get all the points. This one, because the I looks like it's inside, is no good. So the I has to be outside. Because it's kind of confusing out here, I would rather put it here. But I mean, neither here nor there. Just make sure it's outside of the radical. Okay, we do another one similar to that. Say like the square root of negative 100. So 100 is 2 times 50, 2 times 25, which is 5 times 5. Okay, we have a pair of 2s, so that comes out. We have a pair of 5s, so that comes out. And we don't have anything left over, so nothing stays inside of the radical. So in this case, everything comes outside. And 2 times 5 is 10. And again, then just remember that this negative becomes an I. So the simplified form of the square root of negative 100 is 10I. So if it's a non-perfect square, and we have outsides and inside of a radical, the negative inside here just makes it imaginary. Even if it's a perfect square, like 100, which is 10 times 10, the negative inside makes it imaginary. Now, also, do not confuse a negative inside with a negative outside. If I said the negative square root of 100, okay, this negative is outside, does not apply to the inside. So the square root of 100 is just 10, and a negative out in front just simply makes that negative. It's only a negative inside that makes it imaginary. Also, don't confuse a square root with a cubed root. Okay, cubed roots, we talked about this before, can be negative. So the cube root of negative 8 is simply negative 2, because negative 2 times negative 2 times negative 2 is negative 8. If you have an odd power, you can have a negative answer. So again, the imaginary stuff only happens if you have the negative inside of a square root. Now, they will have you do some other things. Okay. Again, a complex number could look like this. Okay, if I said 3 plus 2i, again, we treat I kind of like it's a variable, like it's x. So these are not like terms. We can't combine these. This is considered my real part. Okay, 3 is a real number. We've messed with 3 before. Okay, this is the complex or the imaginary part. So they can have you do operations with that. So for example, if they told you to add 3 plus 2i plus 4 plus 3i or something like that, like any and all math, whenever you're adding, the only thing you can combine is like terms. So if I told you to add 3 plus 2i plus 4 plus 3i, we can combine the real parts and we can combine the complex parts. So 3 plus 2i plus 4 plus 3i would be 7 plus 5i. Likewise, they could ask you to subtract. So if I had 3 plus I or 3 plus 1i minus 2 minus 2i. Okay, again, just like any and all algebra classes, subtraction is adding the opposite. If you are subtracting a quantity, make sure you distribute that negative. So we want to add the opposite. So in any way, 3 plus negative 2 is 1. And remember, if you don't see a number in front, it's a 1. So you've got 1i here. So if I've got 1i plus 2i, that would be 3i's. So they could have you add or subtract complex numbers. Okay. Don't confuse. Now, this reminds me of when we did properties of exponents, but don't confuse addition with multiplication. Addition, okay, simply add like terms. When it comes to multiplying, multiplying is a different animal. Okay. If they told you to multiply these two things together, multiplication requires distribution. You got to multiply 3 times 4, which is 12. You got to multiply 3 times 2i, which is 6i. You got to multiply 2i times 4, which is 8i. And then you've got to multiply 2i times 2i, which is 4i squared. All right. 12 plus 6i plus 8i plus 4i squared, no big deal. However, there is one other little piece of information, one other thing we kind of got to deal with. This I squared does not do what you would think it would do. In fact, it's kind of counterintuitive how this works, but all right, I squared. I'm just going to kind of touch on this real quick, and I'm going to come back to this problem, but I want to work somewhere else so I don't mess up my paper here. Anyway, all right, I squared. So let's talk about this. So first off, I is a number. So we treat it like a variable. Remember, I does have a value. I is the square root of -1. Okay. So if we take I and we square it, that means we're going to take the square root of -1 squared. And if you remember, squaring a square root, those two operations basically cancel each other out. Squaring and square rooting are inverse operations of each other. We cancel them. So I squared is really just -1. So I is imaginary. It's the square root of -1. I squared is no longer imaginary. I squared is real. So it'll just take your number and multiply it by -1. So if we go back to this problem here, 12 plus 6i plus 8i plus 4i squared, this I squared again means -1. So if we take 4 times -1, that just simply becomes a -4. So then if we combine our like terms, we can add 12 and -4 to get an 8. And we can combine our 6i and our 8i to get a 14i. So multiplying, very different from addition. So again, to go back a step, addition, simply combine like terms. Add your real parts, add your imaginary parts. Or add the opposite. Subtraction means to add the opposite, same. Multiplication means distribution. And if you take an imaginary number times another imaginary number, that I squared simply becomes a -1. It takes this +4 and makes it a -4. Anyway, then we go back to combining, add your real parts, add your imaginary parts. This is the proper simplified answer. Okay, I'll do another one of those. All right, if I told you to take 7 plus 3i squared, okay, this one always messes people up because people think they can simply distribute that exponent. Okay, that's not a good property. We went over the properties of exponents. That's not how this works. Remember, if I'm taking a parentheses squared with an addition in here, This means to take 7 plus 3i times itself. So 7 plus 3i times 7 plus 3i. And again, when we multiply, that means distribution. 7 times 7 is 49. 7 times 3i is 21i. 3i times 7 is 21i. And 3i times 3i is 9i squared. And again, that I squared is a -1. So that makes this +9 really a -9. Combine my real terms, 49 minus 9 is 40. 21i plus 21i would be 42i. So again, 7 plus 3i squared is 40 plus 42i. So they're going to expect you to be able to add and subtract complex numbers. They're going to expect you to be able to multiply complex numbers. Now, last but not least, this part actually goes with what we're going to talk about in 7.5, but I can go ahead and introduce it here, and then we'll kind of reinforce it when we get to 7.5. But division. Division of complex numbers gets kind of wonky. All right, anytime we're talking division of imaginary numbers or radicals or something like that, to be considered simplified, okay, there should not be any imaginary numbers in the denominator. That's considered bad. So if they tell us to divide this, we have to do what's called rationalize. And typically you want to rationalize the denominator. When I get to 7.5, we'll talk about occasionally they ask you to rationalize the numerator. That will be for specific instances, but by and large, to be considered simplified, we got to get this imaginary number off of the bottom. This is called rationalization. Now, we can't just magically grab that number and make it go away or move it. To rationalize, we have to multiply this thing by something called the conjugate. You don't need to know the name of it, but that is what it's called. It's basically this same number, but with a different symbol. So instead of 1 minus 2i, we're going to multiply by 1 plus 2i. And I'll show you why here in just a second. But if you have an imaginary number on the bottom, we're going to multiply this thing called the conjugate. Okay? And whatever you multiply to the bottom, you also have to multiply to the top. All right. So if we do this multiplication, 1 times 1 is 1. 1 times 2i is 2i. 3i times 1 is 3i. 3i times 2i is 6i squared. All right, if I clean that up, again, I squared is a -1. That makes that a -6. So 1 minus 6 is -5. 2i plus 3i is 5i. So that's what I should have on the numerator. The numerator is just the top. Okay, same game. Let's clean up the bottom here. So if we multiply, 1 times 1 is 1. 1 times 2i is 2i. -2i times 1 is -2i. And -2i times +2i is a -4i squared. Again, I squared, that's a -1. -1 times -4, that actually makes this a +4. Okay, 1 plus 4 is 5. Now, here's something nifty that happens if we have a positive 2i and a negative 2i. If we add those two things together, they cancel out. That's why we picked this right here. We wanted that imaginary piece to cancel out. That's the benefit of multiplying by the conjugate. You're always going to end up with opposites in here in the middle, and that part goes away. So this ends up being -5 plus 5i over 5. And like we did with properties of exponents, again, normally we could be done here, but if both of these numbers on top are divisible by my bottom, I can divide here. So -5 divided by 5 is -1. 5i divided by 5 is I. So that would be my final answer. I will do another example of that, but you'll see that it plays pretty much the same. So again, division of imaginary numbers, we got to get the imaginary off of the bottom. To do that, you multiply this thing called the conjugate. Same numbers, different sign. Okay? When we do that, that makes the imaginary part go away, so we end up with a real bottom. The top's going to be whatever the heck the top is. And if those all divide out, then we can do so. If not, then that part's considered simplified. So, got that one. I'm going to do another similar problem. So do a plus on this one. So 4 plus I divided by 3 plus 5i. All right, again, to get rid of the imaginary on the bottom, this is the piece that makes it bad. We got to fix this. So we're going to rationalize. To rationalize, we're going to multiply by the conjugate. Same numbers, different sign. If this was a plus here, we're going to use a minus. And again, whatever I multiply to the bottom, I'm going to multiply to the top. All right, so if we do this, 4 times 3 is 12. 4 times -5i is -20i. I times 3 is 3i. I times -5i is -5i squared. Again, clean this up. I squared is a -1. -5 times -1, that makes this a +5. All right, 12 plus 5 is 17. -20i plus 3i is a -17i. It's funny, you don't normally get the same top numbers, but I did it twice just by making stuff up. That's funny. Anyway, do the same thing for the bottom. 3 times 3 is 9. -15i, +15i, -25i squared. I squared is -1. -1 times -5 makes that a +25. All right. Anyway, 9 plus 25 is 34. -15i plus 15i cancels each other out. This would be my answer. But again, these are all divisible by 17. So if I factor that out, I get 1 minus I over 2, because 34 divided by 17, those are all divisible by 17. So that is 7/7. They're going to simplify, have you simplify some negative square roots and get imaginary answers. They're going to have you add some complex numbers. They'll have you subtract some. They'll have you multiply some. They will have you divide. The division, they don't give you very many problems, and they will play out very similar to these. All right, we're going to change gears. 7.5. We're not dealing with imaginary numbers anymore. We're just doing with rationalizing radicals. Again, all that stuff I said about imaginary numbers is true of radicals as well. When you have a radical, square root, cubed root, fourth root, fifth root, whatever, on the bottom of a fraction, this is considered to be not simplified. This is not rationalized. So they are going to ask us to rationalize this. Okay, so in order to rationalize, what we got to do is we got to get that radical off the bottom. We got to multiply. Okay, to get rid of this square root, we're going to make it a perfect square. The easiest way to do that with a square root is to multiply it by itself. Anytime you take a square root times itself, you get a perfect square. And again, whatever you multiply to the bottom, you have to multiply to the top. That makes this a 1, so we're not changing our number. Anyway, square root of 2 times square root of 2, square root of 4, and obviously the square root of 4 is 2. So again, to get rid of the radical on the bottom, specifically, if you take a square root times itself, you'll always get that same inside number. And I'll show you a couple of times where we do that exact same thing and we'll get the same thing. Anyway, 1 times square root of 2 is 1 square roots of 2. Hey, you're going to hear me say things like outside numbers and inside numbers. That's just an easier way to refer to these. But outsides do not combine with insides. Okay, whatever your outside number multiplied to some inside number, they do not combine. The outside stays outside, the inside stays inside. Okay, so this would be 1 square roots of 2 on the top. Same when it comes to simplifying fractions. Outside numbers, this is not under the radical, so this is considered an outside number. Outside numbers only simplify with other outside numbers. You can't mess with your inside numbers here. Okay, so you can't simplify these two. That's bad math. So this is 1 square roots of 2 over 2. Now, you don't always put the 1 in front of the square root of 2. They may just say square root of 2 over 2. But these two things mean the same thing. I think my math lab would actually rather you do this. They don't want the 1 out in front. Just like with a square root, we don't put this index number out in front. A square root's just a square root. You don't write the 2 there. You can, but it's not necessary. Because it's not necessary, we don't want to mess with it. Okay, same thing. So let's say we had 3 square roots of 7 over the square root of 5. Okay, we're not worried about the 3 square roots of 7. That's perfectly fine. What we can't have is we can't have this square root on the bottom. The square root on the bottom is bad. To get rid of that, we need to multiply it. And again, with a square root, we multiply it by itself. Whatever we multiply to the bottom, we got to multiply to the top. Square root of 5 times square root of 5 is the square root of 25. Square root of 25 is 5. Again, if you take a square root times itself, you get itself, no longer a square root. Now, 3 roots of 7 times the root of 5. Again, outside numbers stay outside, inside numbers combine with inside numbers. So 3 square roots of 7 times the square root of 5, this is all multiplication, means 3 square roots of 7 times 5 is 35. Now, again, it feels like we should be able to do something with this. I see that 35 over 5 and I feel like I should be able to reduce. But remember, inside numbers and outside numbers don't play nice together, okay? If the 3/5 reduced, we could reduce that, but you can't reduce the 5 with the 35. This is inside of the radical. This is outside. Now, also, if you happen to have a sophisticated calculator, Most calculators nowadays will reduce radicals. They will rationalize for you. It's really kind of nice. If I hit my fraction button here and I type on the top 3 square roots of 7, just like I had here, and I type on the bottom the square root of 5, okay, and I hit equals, my calculator should do that for me. I get 3 square roots of 35 over 5, which is what we got. So as long as you're just dealing with numbers, no letters, no variables, there are calculators that will do this for you. Okay. The issue we run into is if they give us something like something with letters / variables in it, then all of a sudden now we have to play by the rules. Okay, so should have picked different numbers. Anyway, we'll just do this one because I don't have to mess with this. So same thing, if they make it a giant radical over a fraction, that is the same thing as saying the square root of the one over the square root of the other. So one big radical is the same thing as saying 1 divided by the other. There's no different. So again, what makes this bad is we've got a radical on the bottom that we got to get rid of. Again, we're going to take him times himself. Square root of 5y times the square root of 5y is 5y. Square root of 7x times square root of 5y is a square root of 35xy. Just like with the numbers, we can't reduce the 5 and the 35. This is outside of the radical. This is inside. We can't reduce the y's. This is outside of the radical. This is inside. This is as simplified as this one gets. All right, one of the things they can do to monkey with you or to make this more difficult is, like I've said, when messing with square roots, you can multiply it by itself. When dealing with cube roots, so again, if they change your index number to a cube root or to a 4th root or to a 5th root, okay, it's no longer about multiplying it by itself. Okay, remember when we simplified cube roots, for example, if I told you to simplify the cube root of 8, so this is a different problem. Don't associate this with this. This is just a quick reminder. 8 is 2 times 4. 4 is 2 times 2. And this cube root told me I was looking for 3 of a kind. I was no longer looking for pairs. So the cube root of 8 is 2. Again, I'm looking for 3 2s. So kind of the same idea. So if I need to get rid of this cube root on the bottom and make it just a real number out here, okay, the idea is I need 3 5s. Right now I've got 1. So I need to multiply it by what would essentially be 2 5s. 5 times 5 is 25. Okay. So to get this cube root to be a whole number, I need to multiply it by, okay, the squared version of this. I should have done that in red like I did all the other ones. And same thing, whatever you multiply to the bottom, you got to multiply to the top. So the cube root of 5 times the cube root of 25 would be the cube root of 125, which again gives me my 3 5s, which is what reduces to the 5. That's how we made that work. I'll do another example and show you again with different numbers, but the rest of this plays the same. Outside numbers stay outside. Inside numbers, 2 times 25 is 50. So this would be 3 cube roots of 50 over 5. Okay, again, dealing with cubed roots instead of square roots. What we want is to get rid of the number inside. I want to end up with, I'm going to multiply. I want to end up with a whole number outside of the radical on the bottom. Now, with this one, we can kind of play around a little bit. 4 is 2 times 2. So again, with a cubed root, you need 3 of a kind. So what I need is I need another 2. And likewise with variables, 3 goes into 2, it doesn't. So I need 3 to go into something, so I need another x. So that if I were to multiply these, I would get the cubed root of 8x cubed. So 8 is 2 times 4, which is 2 times 2. So all those 2's would come out. 3 goes into 3 one time. So again, cubed roots play a little bit differently. You don't always want to multiply it by itself. Square roots, you always want to multiply by itself. Cubed roots, you got to figure out what you need to get 3 of something to get it out of the bottom. Anyway, whatever you multiply to the bottom, you're going to multiply to the top. So again, an outside number stays outside, an inside number stays inside. All right, last but not least with rationalization is if they give you something where you're adding or subtracting on the bottom, if you see a plus or a minus down here with a radical, we've got to do the same thing we did with the imaginary numbers. The only way to get rid of the square root of 5 here is to multiply by the conjugate. If you try just multiplying by the square root of 5, when you distribute, you're still going to end up with a radical on the bottom, and we don't want that. So when you have a plus or a minus down here, that's when we're going to do that thing and multiply by what's called the conjugate. Again, I don't care if you know what that's called. You just need to understand that it's going to be these same numbers, just with a different addition or subtraction symbol. So if the original problem had 2 minus the root of 5, I'm going to multiply by 2 plus the root of 5. And again, whatever I multiply to the bottom, I'm going to multiply to the top. I'm actually going to do the bottom first this time to show you how that gets rid of the radicals. Again, 2 times 2 is 4. 2 times the square root of 5 is 2 square roots of 5. 2 times the negative square root of 5 is negative 2 square roots of 5. Square root of 5 times itself is 5. Positive times a negative is a negative. Okay, come down here. If I clean this up, 4 plus negative 5 is negative 1. Positive 2 roots of 5 and negative 2 roots of 5 actually cancel each other out. So that got rid of my radicals on the bottom. So I went from having a square root on the bottom to now being only whole numbers. Nice. Okay, if we do the top, again, we got to distribute. Root of 3 times 2 is 2 roots of 3. Root of 3 times the root of 5 is the root of 15. 2 times 2 is 4. 2 times the root of 5 would be 2 roots of 5. Now, it looks like we should be able to do some stuff with this, but actually none of these things are considered like terms, so none of them combine. So the top would still look like all of these individual radicals. Nothing combined, so it's 2 roots of 3 plus the root of 15 plus 4 plus 2 roots of 5. So we would end up with this whole big, ugly answer. And actually, because we're dividing by a -1, okay, if we had some other number that wouldn't reduce, we're fine, but anything over 1 is itself. Because it's negative, this just changes the sign. So we would actually get -2 roots of 3 minus the root of 15 minus 4 minus 2 roots of 5. So if they give you a plus or minus on the bottom, you've got to multiply by that conjugate. It's the same game. I'll do one more example of that, but I'm actually going to change it up just a little bit. Okay, and again, this is going to move kind of against what we had talked about, but pay attention to the directions because in my math lab, they do this a couple of times. Okay. This problem is good. Okay. We do not have any radicals in the bottom. We are what would be considered simplified. However, sometimes in the directions, what they'll say is they'll tell you to rationalize the numerator. Now, I will not put any of these on your test. I will only have you rationalize the denominator because that's what you're supposed to do. But there are a couple of problems in my math lab where they're going to tell you to rationalize the numerator. What they want is they want to get rid of the square roots in the top. They're saying you can put them in the bottom, no problem, but get them off of the top. So if they tell you to rationalize the numerator, it's the same game. We just got to get rid of the radicals in the numerator. So we look at this, and this is what we're going to use. So we're going to multiply by the conjugate of the top. Square root of x times square root of x is x. Positive roots of x, or positive roots of 5x. Negative roots of 5x. And then negative root 5 times positive root 5 is -5. So again, if we clean that up, those cancel each other out, and we're just left with x minus 5. If we distribute here again, outside numbers stay outside, so we would end up with 2 roots of x plus 2 roots of 5. Those are not like terms. We can't combine them. They stay just the way they are. So if they ask you to rationalize the numerator, they'll only do this a couple of times. If there's like 3 problems, I think, in my math lab where they tell you to rationalize the numerator. That just means they want to get the square roots off of the top. All right. The last thing that we have to cover tonight is 7.6. 7.6 is all about solving. I actually like this section the best because we get answers. It's no longer these, I don't know, goofy simplified square roots and imaginary numbers all over the place. We're actually going to solve for something. All right, if they give you a radical equation to solve, okay, step 1 is to isolate the radical. Okay, that means get the square root piece or the cube root piece or the 4th root piece, whatever it is, get it by itself. You don't want any numbers out in front. You don't want numbers hanging out the back. Okay, you want only the square root piece all by itself. Okay, then you're going to use exponents to cancel the radical. So if this was a cubed root, we would use a cubed power. If this was a fourth root, we would use a fourth power. To get rid of a square root, we use the squared power. So we would square both sides. Squaring a square root, get rid of it. So that's going to leave me with just what was inside. And then 5 squared is 5 times 5. That would be 25. Once you get rid of the radicals, we can just solve. This is a typical linear algebra problem. Subtract 2 from both sides. 3x equals 23. Divide, divide. X is 23/3. Now, I'm going to recommend that you go ahead and check your solutions. Most of the time, it's not a big deal, but every once in a while, they're going to throw some problem in there where you're going to do all of the math right, but this answer doesn't necessarily check out. This one does. If we plug this number in, 3 times 23/3 is 23. 23 plus 2 is 25. The square root of 25 is 5. This one checks out. But I would recommend you go ahead and check your solutions. I'll show you a couple of problems where they throw you a curveball and either one or another solution does not work, but that's something you should be able to do. All right. Negative square roots of 2x plus 7 equals -3. That plus 7 is outside of the radical. So again, step 1 is to isolate the radical. We got to get the square root piece by itself. We do that by adding the opposite, all the typical algebra stuffs. So I want to get rid of this 7, subtract 7 from both sides. Same, I need to get rid of this negative, so I'm going to divide by a -1. And I get the square root of 2x equals 10. Same game, to get rid of the square root, I'm going to use the squared power. Cancels, so I get 2x, 10 squared is 100. 10 times 10 is 100. Solve for x. 100 divided by 2 is 50. Again, shouldn't need to check this one, but it does work. 2 times 50 is 100. Square root of 100 is 10. -10 plus 7 is -3. If they change the index, the only thing that changes is the exponent you would use. If they gave me a problem like so, the fourth root of 3x minus 2 equals 2. To get rid of a fourth root, we use a fourth power. So again, those two things cancel each other out. So I would just have 3x minus 2. Now, 2 to the fourth power. Remember, you're not just multiplying 2 times 4. That means 2 times 2 times 2 times 2. It's 2 times itself 4 times. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So remember, you're actually taking this number to this power. Anyway, go to solve, add 2 to both sides. 3x equals 18. Divide, x is 6. All right, where this starts getting a little uglier. When we've got x's outside of the radicals too. So for example, if they said something like this. Okay, square root of 46 minus 6x equals x minus 5. Doesn't look too dissimilar from problems we've done until we go to square both sides. So again, to get rid of a square root, we're going to square it. Means I got to square this side. So we get 46 minus 6x. However, remember, x minus 5. If we square this quantity, that means x minus 5 times itself. And then we've got to do that distribution. So x times x is x squared. Negative 5x and negative 5x is negative 10x. And negative 5 times negative 5 is positive 25. Now, it's been a minute, but you guys remember when we have an x squared, that's called a quadratic. Solving quadratics got a little ugly. So remember, what we got to do is we got to set this equal to 0 to solve. So we need to get both of these guys over here. So if I subtract 46, 25 minus 46 is negative 21. If I add 6x, negative 10x plus 6 is a negative 4x. Then we have that x squared. All right, when you have a quadratic, remember, to solve, we got to factor. So x squared is x times x. And then what multiplies to get negative 21? It also adds to get negative 4. That would be negative 7 and positive 3. Set your factors equal to 0 and solve. Add 7 to both sides. X could be 7. Subtract 3 from both sides. X could be negative 3. Gross. So when you have an x on the outside and you go to square, you end up getting this quadratic. Remember, anytime you're solving a quadratic, you got to set it equal to 0, add a factor, set your factors equal to 0, and solve. Also, when you have an x on both sides, this is where you definitely need to check your solutions. Okay, I'm going to walk you through this one. If I plug my 7 in for x, okay, so again, I have an x here and an x here. If I plug my 7 in, we can see if this works. All right, 6 times 7 is 42. 46 minus 42 is 4. Square root of 4 is 2. 2 equals 2. 7 checks out. Okay, 7 is a valid solution. If I check the negative 3, negative 6 times negative 3 is 18. 46 plus 18 is 64. Negative 3 plus negative 5 is negative 8. The square root of 64 is positive 8. Positive 8 does not equal negative 8. These do not equal. This is not a valid solution. So we did all of the math correct. I promise everything up here is correct with no mistakes. Yet one of the solutions I got does not work. There's no way to fix it. There's nothing you can do to it. It's just not a valid solution. So this 7 is the only valid solution. So you've got to be careful. There are some problems they're going to throw in here where you could end up with one or none solutions. Got to check. All right, the last problem they may potentially give you is one like so. square root of x plus 4 equals square root of 2x minus 3. If you have two different radicals, no big deal. Okay, typically we want to isolate the radical. Now we've got two of them isolated. To get rid of the square roots, we still square. That still conveniently cancels those things out. So I get x plus 4 equals 2x minus 3. And again, this is just a straight up linear algebra problem. Get your x's together on the same side. Get your constants together on the same side. And x equals 7. Check it to see if it works. 7 plus 4 is 11. This is the square root of 11. 3 times 7 is 14. 14 minus 3 is 11. This is the square root of 11. So this one works as well. So that basically takes care of 7-6. So that finishes up chapter 7. So next week, the only days the school is open is Monday and Tuesday. I'm obviously not going to expect you to test over those 2 days. We will test the following week. So use this next week to make sure you're caught up on your stuff. Okay. Do your homework, be ready to go. We will test over chapter 7, not next week, but the next week. The following week, we will finish up with chapter 8. Then all we have left is the final. So again, you're going to want to finish strong. Make sure you end up in a good place. That's all I got for you. If you have some questions and you want to stick around and ask them, I'll be here for a little while. But if you're done listening to me and you're ready to go, that's all I got for you. You are free to skedaddle. So we'll see you guys. So again, enjoy your Thanksgiving next week. The following week, we will test over chapter 7. See ya.
We don't have class on that Thursday too.
No, we won't have class. Well, I'll be here for that test. So if you want to come in and test, that's fine. I'll be here. Yep.
Just make a point.
That's fine.
Have a good one.
All right, we'll see you.